Okay, reaction number 6, very, very similar to ester hydrolysis, is amide hydrolysis. Just a couple of things to keep in mind. This is a lot slower. Okay, so it's a lot slower. And the reason why this is a lot slower is because, first of all, this NHR, it's a pretty poor leaving group. It's a worse leaving group than an alcohol of the similar structure. The next thing to keep in mind is there's also electron donation via resonance. So what that does is it lowers the electrophilicity of this carbonyl. And if it lowers the electrophilicity of this carbonyl, you can have nucleophilic attack happening as quickly. 3 scenarios to deal with. One is when you're under basic conditions, your pH is greater than 7. Here you're going to be using your OH- as your nucleophile. And then the second thing to keep in mind is this NHR is such a bad leaving group that you need to activate it even though you're going to have an O- on the tetrahedral complex. Okay, so the thing is, we're trying to use H2O to protonate a nitrogen, and that's just going to be really, really slow. So basic conditions for amide hydrolysis, not really going to happen very, very well. Okay, acidic, there's a considerably, it's going to be faster. pH is less than 7. First of all, point 1, we activate the carbonyl by making it more electrophilic, protonate the oxygen. Number 2, H2O is going to be the nucleophile. And then 3, because we are under acidic conditions, we can activate the NHR to make an NH2 plus R, which is a better leaving group. Okay. However, even though this is positively charged and you have this HO group right here, you can't push it out like you did with ester hydrolysis. So instead, you're going to need a negative charge in order to push this thing out. And what we're going to do, and this is actually what kind of makes this acidic hydrolysis also pretty slow, is that you have to use H2O as a base. And what that H2O is going to do is it's going to pluck off this H. Then you're going to have a negatively charged oxygen. The negatively charged oxygen can now push out this NH2 plus R, which is not that good of a leaving group. Okay, so that's what happens under acidic conditions. It's going to be faster than basic conditions, but it's still going to be pretty slow compared to ester hydrolysis. And the third type of situation you want to deal with is general base catalysis, and this is going to be what you do if your pH is equal to 7. Most common amino acid I would pay attention to and be able to draw for this would be histidine, because remember, around 7, its pK is around 7, so the histidine residue could be protonated or deprotonated, and that's actually what we want to happen around a pH of equal to 7. So the first thing that's going to happen is the base, a deprotonated histidine is going to pluck the H off from an H2O to give you OH-, and this is a better nucleophile. And then the resulting BH+, what this can do is this can activate your leaving group. Okay, it can activate your leaving group and make it more easily available to leave. Okay, we don't need to deprotonate an OH because we are at a pH of equal to 7, so we're not going to have this oxygen protonated like we did with the acidic conditions. So then from there, the negative oxygen is strong enough to push out this leaving group, and boom, you got your amide hydrolysis. Okay, so again, amide hydrolysis, pretty similar to ester hydrolysis. It's a little more complicated due to the fact that you have a poor leaving group, and it's going to be slower for all these reasons listed, and also just the fact that this carbonyl, it's not as electrophilic. All right, so there we have it, amide hydrolysis.